And we're back, and we're going to flip through a couple of questions here, and then we'll move on into refraction. And the first question asks, if we have an object that's placed 20 centimeters in front of a plane mirror, and again, remember plane means flat, okay? So if I have an object that's placed 20 centimeters in front of a plane mirror, then the image of the object formed by the mirror is going to be where? 10 centimeters in front of the mirror, 10 centimeters behind the mirror's surface, at the mirror surface, 20 centimeters in front, or 20 centimeters behind. Well, remember, okay, come back up here, and remember that wherever the object is with a flat mirror, the image is going to be behind the mirror, and it's going to be equidistant. Okay, so with that in mind, the answer here is going to be 20 centimeters behind the mirror's surface. All right. If we have parallel light rays from a distant object and it strikes the surface of a concave mirror, after leaving the mirror's surface, what will happen to the rays? Okay, they will converge toward the what? And the answer here is going to be the focal point, right? Actually, I want this picture right here. So the light rays are going to converge generally at the focal point in this case, okay? So that is the answer to that question. And what about true false? If we have a curved mirror that produces an enlarged image, we'll always have a greater field of view than a plane mirror, okay? Now, this one is false, right? So this one is false, and the reason being, remember that enlarged images have smaller fields of view, okay? Now, they obviously have smaller fields of view than the convex case, and we're actually comparing a concave mirror with a flat mirror, but the flat mirror is still going to have a larger field of view than the concave mirror. And so in this case, this question is false, right? And finally, for the think pair shares, the primary mirror in an astronomical telescope must be, out of all of these, a convex mirror. Now, specifically, it's almost always going to be a parabolic shape, but in general, it will be a concave mirror, okay? It will be concave. Okay, so that concludes reflection, and now we want to move on to the case of refraction. Okay, so again, this chapter is all about how light interacts with surfaces, and in the case of a mirror, it's almost all completely reflected. There can be a little bit of absorption, but it's essentially all reflected. And in the case of refraction, refraction occurs, and most of us have seen something similar to the pencil in the water, right, where it looks like the pencil gets kind of cut in half there. And what's happening is that as the light meets the boundary, okay, between the medium that it's propagating in originally and then through the medium that it gets refracted into, the path of the light changes. And that's why you see the pencil seem to get cut in half. So, for example, let's say that I have a glass and an air boundary, okay? And I have a ray moving through the glass, and it hits the boundary between the air and the glass. Some of that light ray is going to get reflected just like a mirror, and that reflected ray is going to be subject to the law of reflection. And then the transmitted wave, or the transmitted ray that crosses the boundary is going to change direction, okay? Now, we'll talk about why that happens here in just a moment, but for the moment, that is what actually occurs, okay? So what does the law of refraction say? So the law of refraction says A light ray is bent toward the normal when it enters a transparent medium in which it travels more slowly. It's bent away from the normal when it enters a medium in which light travels faster. So what's going on here? Okay, so in the cases of these mediums, and the mediums can be whatever the light is traveling through. In this case, we have air and we have glass. So what this statement is saying, if I have a transparent medium in which light travels more slowly, which one of these is that going to be, the glass or the air? Well, in this case, it's going to be the glass, and it's going to be the glass because the glass is of higher density, and as the light moves through the glass, it's going to experience more opposition. It's going to bump into more things. There's more things for it to bump into and get slowed down with. So that is why the speed of light is less in the glass than it is for the air. Now what happens, what happens is that as the light moves from the more dense medium in which light travels more slowly to the medium in which light travels faster, what happens in that case is that, this would be going from glass to air, for example, what happens is that if I were to draw an imaginary normal here, then the ray is going to get bent away from the normal. If I go from more dense to less dense, the ray gets bent away from the normal. And if I do the opposite, if I go from less dense to more dense, then if you look over here, then the ray comes in and it actually gets bent towards the normal inside the more dense medium. And that's basically what the law of refraction says. Now, what are some consequences of refraction? What are some consequences of refraction? Well, one consequence is that things aren't always as they appear. And for example, if I have a coin at the bottom of a glass and I pour water into that cup, the coin actually looks a little bit bigger. And why does the coin look a little bit bigger? So if I have a coin in my glass, then the light from the coin is going to travel, and when it hits the boundary, it is going to expand outward, It's going to expand outward, and as it expands outward, the apparent position of the coin changes, and so the apparent position of the coin is shifted upward, and so it looks like it's closer. So the apparent position of the coin changes because the light rays diverge at the surface, and that divergence correlates with shifting the position that it looks like the light rays actually were generated from. So when you see things through water, if you're looking from air into water, or if you're in water and you're looking out into air, things are going to look slightly different than they actually are due to the way that the light rays are going to get bent moving between the two media. So the way that the light gets bent, is dependent on how much the speed of light changes. And we call this the index of refraction. So the index of refraction, say for glass, a typical index of refraction for glass is about 1.5. So what that means is, if I take the speed of light in vacuum and I divide it by the speed in that medium, in the glass, I'm going to get a ratio of 1.5. So what that means is, if you kind of look here at the glass, the speed of light in air is 3.0 times 10 to the 8th meters per second. So in a gas like carbon dioxide, it is not hardly slowed down at all. It goes from 3 times 10 to the 8 meters per second down to 2.9966. Not very much. But as you move down into liquids and down into the solids, you can see that that value adjusts quite a bit. So the crown glass, for example, has a speed of 1.97 times 10 to the 8 meters per second. And if I take 3.0 times 10 to the 8th and divide it by 1.97 times 10 to the 8th, I'm going to get something very, very close to 1.5. And so the index of refraction for glass, a typical value, it really does depend on the type of glass, how thick the glass is, the density of the glass, etc. But a typical representative value for the index of refraction of glass would be that 1.5 number. Okay, and that number is found by taking this experimental speed in the medium and dividing it into the speed of light so that you always get a ratio larger than 1. Okay. In air, we typically take that speed to be the same as the speed of light, so air does not really slow down light propagation hardly at all. As far as the light is concerned, it doesn't really notice the air very much at all. Okay, so if you are looking at a problem and you see that one of your mediums is air, then you can go ahead and assume that the index of refraction is 1, and by extension that the speed of light is going to be 3.0 times 10 to the 8 meters per second. Okay, so briefly here, why does the light bend in the first place? Okay, so if I think of my incoming ray as a set of wave fronts, okay, if I think of my incoming ray as a set of wave fronts, when those wave fronts hit the medium, when they hit the boundary between the two media, the total amount of energy per unit time crossing that boundary has to stay consistent. But it is dependent on the frequency of the wave. And the frequency cannot change if energy is to be conserved. If energy were not conserved, or if the energy were not constant crossing the boundary, then energy would be piling up somewhere and or being lost. But that doesn't happen. And so since that is the case, the frequency has to stay the same. But because the speed of light changes, then if the frequency stays the same and the speed of light goes down, then that means the wavelength has to go down. And so the only way that you can get the wavelength to shift and decrease is if it actually bends once it moves into the new medium, into the more dense medium. The exact opposite case will occur if it goes from the more dense medium to the less dense medium. So these wave fronts have to compress in wavelength so that the actual frequency stays the same, but the speed of light decreases. And so recall that there's an equation that relates speed, wavelength, and frequency, and it is speed of light equals the wavelength of an electromagnetic wave multiplied by the frequency of an electromagnetic wave. And so since the frequency has to stay the same, if the speed goes down, therefore the wavelength has to go down as well. But that means that these wave fronts get compressed as the wave is moving in for the frequency to stay the same. And it's that bending of the wave to conserve the frequency that causes the actual bending. Okay, so that is why refraction occurs in the first place when there are multiple media that the light is moving through. Alright, I'm going to leave that there for this video, and next time we will actually talk about some of the results of experiments involving refraction. Alright, we'll see you next time.